For my first topic, I chose to focus on work and power. Inspired by our short lab, Your Power, I wanted to conduct my own experiment by running up a hill, the second time carrying a backpack with additional weight. When analyzing the video, I will use the following equations to determine which trial generated either more work or power. First, we should understand what work and power mean. Work can be defined by the amount of energy transferred by giving energy to something or taking energy away from something. Power measures the rate at which someone, like me, or something such as a car or an automobile, does work. In the table above, you can see that first I calculated the force by multiplying my weight with gravity, which is 9.8 meters squared. Next, I calculated my work in each trial by multiplying the force with the distance I ran. Finally, I calculated my power, dividing the work by how many seconds it took me to run up the hill. By carrying an extra 7 pounds, we can recognize from my data that the amount of work as well as the power generated in the second trial increased. In my first trial, without a backpack, I produced 376 joules less in my second run. Additionally, from my calculated power, I generated 725 more joules by carrying 7 pounds. For my second experiment, I recreated our collision lab by kicking a soccer ball into another soccer ball, and then, for my second trial, kicking the same soccer ball into a basketball. The first collision was an elastic equal mass collision, because the two soccer balls had the same mass. My second trial was an elastic unequal mass collision, because I kicked one lighter object, my soccer ball, into a heavier object, my basketball. I recorded and used video analysis to calculate if energy was conserved, in addition to my error analysis. I used the data from my Logger Pro analysis to calculate the velocity of both balls before and after the collision using the first equation shown. I then used this data to find the total momentum of each ball before and after each collision using the equation for momentum. This led me to calculate the ratio of momentum by comparing the total momentum before and after the collision. In elastic collisions, both momentum and kinetic energy is conserved because the first object either comes into complete stop or recoils. Therefore, because the first ball maintains form and detaches from the second object, no kinetic energy is lost and the system conserves its kinetic energy. The law of conservation states that if the momentum is conserved before and after the collision, then the ratio is the same. This means that for all of our runs, the ratio should have been 1:1. Our first trial depicts an elastic collision without a recoil because there's an unequal amount of mass in the first ball as well as the second. When looking back at my calculations, I can see that the law of conservation did not reflect in my data. For my first trial with the two soccer balls, my ratio of total momentum was 12 to 2.6 instead of 1:1. When contemplating what could have gone wrong, I can think of two possible issues. Firstly, the soccer ball that got hit was slightly deflated, which likely impacted how fast it moved after the impact. Secondly, I did my experiment on the grass. This additionally could have caused the kinetic energy to be lost to the friction and heat. During the second run, the first ball recoiled due to the increased weight in the first ball. Yet again, after my collisions, the ratio was 15:4, showing that after the collision, the basketball did not maintain the same momentum as the soccer ball did. I think the grass could have affected this trial run as well, by causing the kinetic energy to be lost to the friction and heat. Although my experiments did not fulfill my expectations or perfectly show the law of conservation, I made do with the materials I had, and it was clear that the surroundings of my experiment could have affected my data and my conclusions.